The next topic in our study of vector functions is to do derivatives and integrals of vector functions. So we're going to do derivatives. We're going to just learn what are the various differentiation rules for vector valued functions. And then we're going to do also integrals of vector valued functions. None of them are particularly difficult. It's just an extension of things we have already done. What does it mean, a derivative of a vector valued function? Well, it's just the same thing we've done before. So if I have a vector valued function, our t at t is this value, and I'd say t plus h, there is this value, and as h goes to 0, the difference of the two values will go to, will be like this, like this, like this, like this. And the limit will not be a number in this case. The limit will be a vector. Every time I do, if I define derivative like I usually do, I want to know what's the rate of change of this vector function. The rate of change will be some vector, not a number. So if you just define it as we usually do, as a limit, then you see that the difference of these two is a vector minus a vector. So it's a vector and then scaled by h. But it's still a vector. And the solution to a derivative of a vector valued function is another vector. What vector? So this is the case when h is positive. When h goes to 0, the answer will be this red vector, which is the tangent vector of the curve at that point. Okay, so it will give me a way to find tangents. Once I have parameterized a curve, I will have tangent vectors at any point for that curve. Okay, so that is how we're going to use these derivatives, is to find tangents at points. So how are we going to find derivatives? If you carry out the derivative, this limit, what happens is that if we think of R, as I did before, as a sum of a vector in components in I, j, and k, and if I do this process, what you get is that you're going to get the derivative of each one of the components if those exist. So whenever you have a function, a vector valued function, that the components are differentiable, then the derivative is just going to be the derivative of the components. So what that says in plain English is that when you take the derivative of a vector valued function, you just take the derivative of each component, and that's the derivative. One more thing that we're going to compute is the unit tangent vector. If you remember, when we did directional derivatives, to find a directional derivative, we used unit vectors. So to find a derivative in one particular direction for a function, we used a unit vector. So finding not just the tangent vector, so if I have a curve, something like this in space, the tangent vector here might be something like this. The tangent vector is not only giving you a tangent direction, but it's also giving you at what speed you're traveling at that point. It's not giving you only like at what speed a number, but the direction and the speed at the same time. So the tangent vector, just the derivative, can be really large in magnitude, but many times because of, for example, directional derivatives and so on, we want another vector that is in the same direction, but of length 1. Okay? And that is what this does for you. If you found the derivative, if you divide by the length of the derivative, then you get what we call the unit tangent vector, which is a gadget we'll use later to do other calculations with. Okay, so let's do some examples. Let's find the derivative of the function given by our t is this function, and find the unit tangent vector at t equals to 2. So, as I said, to find the derivative, you just take derivatives component by component. So what is the derivative of 1 plus t? And by the way, by prime, we're doing d dt of r of t. What's the derivative of 1 plus t? 1. 2 plus 5t? 5. Minus 1 plus 66. So what that says is that the derivative is constant. So that means that my velocity is constant in that direction. Why? Because this is describing a line. And if I'm traveling in a straight line, my speed is always going in the same direction. We could change the speed so that I'm accelerating on that line, but the way this is parameterized, it is a linear motion, and the velocity is constant. Okay? So I'm not going to draw it to scale or anything, but the line is somewhere like that. And then at any point, we have the same derivative, and it's the vector that is pointing in that direction all the time. Okay? In particular, they tell me find the unit tangent vector at t equals to 2. So how do I do that? First of all, I find the derivative at 2. It's constant, so it's exactly the same one, 156. And then to find the unit tangent vector, you see this is not length 1. So to find the unit tangent vector at 2, I'm going to have to do r prime 2 divided by the length of r prime of 2. What is the length of this thing? Is 1 squared plus 5 squared plus 6 squared. Whatever that is. That's 36 plus 25, 61. Is this 62? Think so? So it will be 156 divided by the square root of 62. So the unit tangent vector is 1 over the square root of 62, 5 over the square root of 62, 6 divided by the square root of 62. Okay, so those are the two things that we're looking for. It's the derivative and the tangent vector at 2. Okay? All right, let's see something that is not just constant speed. What about the spiral we had before, this helix going up a cylinder? Let's look at what is the derivative. The derivative of cosine is minus sine. The derivative of sine of t is, and the derivative of t is. And let's find the tangent vector at t equals pi over 2. So what happens if I evaluate at pi over 2? At pi over 2, sine of pi over 2 is 1, so I get minus 1. Cosine of pi over 2 is 0 and 1. So let's see if that matches our intuition of this helix. So we started here, and then it goes up here. How long? Pi over 2, we are here. If you compute what is r of pi over 2, where are we at pi over 2 time? We are at cosine of pi over 2. No, the pi over 2, the cosine is 0. The sine of pi over 2 is 1, and pi over 2. Okay, so that's where we are at pi over 2, and then the direction given by the derivative is the tangent direction, which is minus 1, 0, 1. So it's this direction. So it's telling me that the tangent does look like that. Okay, which it does. The curve keeps going like that, but at that point exactly, that is the tangent direction. Okay, and then for a unit vector, I'll have to do the derivative at pi over 2 divided by its length. And the length of this vector right here is the square root of 1 squared plus 1 squared, so the square root of 2. So the derivative at pi over 2 is minus 101, and then I have to divide by its length. I computed the length of that vector, and then I use a different one. So it is minus 1 over square root of 2, 0, 1 over the square root of 2. Yes, thank you. Thank you for noticing. So what rules are there for derivatives of vector valued functions? They look exactly the same as you would expect. The derivative of a sum is the sum of the derivatives. The derivative of a constant times a function is the constant times the derivative. The derivative of a function times a vector. So if there was a function multiplying all three coefficients, then that one can come out. And then there will be a product rule, the derivative of f times the vector plus the function times the derivative of the vector. So that's just a product rule. Maybe I'll write it here, product rule. Then what happens if I do the derivative of a dot product of two vectors? There is some sort of product rule for dot products. It's the derivative of u dot with v and u dot v prime. So let me just indicate here that these dots, here, here, and here, those are the dot product. Okay? Then this is a formula for cross products, and there's also a chain rule that we can use if we're doing derivatives. Finally, I'll mention that if the length of the vectors is constant, then the derivative is orthogonal to RT. If the length is constant, what this means is that it is going in it's moving in a sphere. Okay, if the length is constant, all the vectors that are images are in a sphere, so it's some path in a sphere, so it's some spherical motion. And whenever you're in the sphere, all the derivatives will be orthogonal because the derivative in a sphere, if you're at a point in a sphere, the derivative is perpendicular to the diameter that points to that point. Okay. Last but not least, we can do derivatives of vector valued functions. If I want to take we can do integrals of vector valued functions. You would define them just like you would define them with a Riemann sum. But again, because these functions can be expressed as a function in ij a k, when you do the partial sums, these Riemann integrals, you get the Riemann integrals of each coordinate. So what happens is that if you are going to integrate a vector valued function, you just throw the integral in each coordinate. So as I said, there's nothing new happening. You just do 3 integrals instead of 1. So for example, if I want to find the integral from 0 to pi over 2 of RT, and RT is the helix that we had before, I would do the integral from 0 to pi over 2 of R of t dt is going to be 3 integrals from 0 to pi over 2 of each one of the components. And if I want to do those integrals, what do I get? I get the integral of cosine t, that is sine t between 0 and pi over 2. This would be minus cosine t between 0 and pi over 2. And this would be t squared divided by 2 between 0 and pi over 2. And if you evaluate this, I get 1, 1, and pi over 2 squared divided by 2. So I get a sum. It's just doing some integrals. I'm adding sort of like what is the total sum of positions as you've moved along that curve.